So we come to the real thing, shortest path, and what role they play in computer vision. And here on this page, I'm giving you a few sample applications, a generic algorithm, and then we will look at the modeling in more detail. Yeah? So sample applications in computer vision, I'm going broadly from the more simple to the more complicated. So very simple one, find its use in tools like intelligent scissors in GIMP or magnetic lasso in Photoshop. So here the idea is that you click on a few points of the outline of your object, and then the line will somehow snap to the object. It's not a routine that I would recommend using in practice for many reasons. Now, look at this image. I mean, this is as simple as it gets, brown goat in front of a perfectly homogeneous background. Even in this tutorial example, you see there's a mistake here. So they should have put one more point there. So one leg is missing. So you see it's a highly, it really requires a lot of interactions. And we can do better than that today. And for example, in Office nowadays, you would probably do this with something called GrabCut, invented by Carsten Rutter. So it's not what you want to do nowadays, but it shows you the basic idea, namely that we click on 2 points, let's say this one and this one, and rather than connect by a straight line segment, we can compute a cost matrix where image boundariness would be low cost and a homogeneous area such as the sky here has a high cost. And then we find shortest path or a geodesic path from this point to that point, which in this case snaps nicely to the object boundary. If you use somewhat more clever, if you use a little bit of intelligence in defining this boundary image, then you can do things like here. We have some input image. We have here some inputs, namely blue. The blue stroke said this is inside, and the green stroke, notice that one green stroke was not enough. It needed 2 green strokes to say this is outside. Then this image here is essentially a similarity to a pixel-wise similarity to how similar am I to the blue class. Well, you could call it a classifier, except it's something really, really super simple. But think of it as training a pixel-wise classifier that asks for each pixel with which probability do you belong to the blue class or to the green class, and this is the output. And then in this image here, we can ask for each and every pixel how far. So if I now find the shortest path, where cost of a path is given by sum of edge weights, to the closest blue point or to the closest green point, so from these annotations, then this will define me a segmentation, a seeded segmentation. And what we see here on the right-hand side are then for each pixel those distances. Yeah, so for any pixel, let's say for this pixel here, it will find the cost of the path to the closest blue annotation, and the cost here is fairly low, as we see, because everything here is blue. And for the same pixel, we can ask what is the cost of reaching the closest green annotation, and this cost is much higher. Here, these are all false color plots where blue means low, green means intermediate, and red means really high. And based on that, you can obtain a segmentation. And the segmentation you see here, this is the outline on the left-hand side. In fact, in this particular case, people did not a hard segmentation, so assigning a pixel either fully to foreground or fully to background, but they used a so-called matting, which close to the boundary area allows partial assignments to foreground or background. And this image matting is really important if you cut out people who have more hair than I, and because if you do so you want to cut out the person from the background, and if you do this without matting, then either you will be conservative and you cut off the hair but also part of the head, or you get all the hair, but then between the hair you can still see the color of the wall that was in the background. And then if you take this person with all their hair and the background wall and you paste them into another image, this will look weird. Yeah? And the matting here is a process that helps a little by by using transparency, let's say. Good. There's a question in the chat. How is the distance defined? All right. So the color similarity was used to generate this picture here. But now this picture, it's a gray value picture. So let's imagine this. So what the brightness here shows is the cost of making a step in the direction of the blue annotation. So if we our similarity to blue, let's say. And then on that kind of image, we will find paths which run over as few dark pixels as possible. And there's a question, how stable is it with varying brightness? Well, so of course the annotations here, you need to give a new for each and every image. And now it's up to the cleverness of the classifier or how much training data it has seen outside the single image, if or not this image will be easy to work on or not. I'm being vague here, I know. Let me anyway move on. I think the question about combinatorial distance will become, I think I will answer it a few minutes down the road. All right, I want to give you another example, completely different. Here we have two camera images taken from a left and a right camera, and the task here is to estimate a depth map from those two images shown here, and it will turn out that shortest path computation is used to make, well, even this estimate here, which still looks pretty terrible, that is already the output of a smoothing process, which involves shortest paths. And this map would look a lot worse without that kind of smoothing process. And the last example application, and I will mention each of these in more detail down the road, just to give you an overview. The last example application here is segmented least squares, where we're given a number of input points. You see these black points here. And we now define a penalty for making a jump. And then we're trying to estimate a signal which is either piecewise linear or in this case piecewise constant, which within each of these segments, we want the sum of squared deviations of the observations from their respective mean to be as small as possible. And on the other hand, to make that as small as possible, we would just include one jump between any two observations. but at the same time we impose a cost on jumps. So we want something that is piecewise constant, but we don't want the pieces to be too tiny. And this is an optimization problem, which it turns out can also be solved in terms of shortest path. All right. Now, shortest path algorithms are maybe the most important problem that is routinely solved using an approach called dynamic programming. What is dynamic programming? It is essentially a clever way of storing and reusing partial solutions. Now, when does this work? You need, you must have one ingredient, and it only makes sense if you have the other ingredient. The must-have ingredient is this, namely, I want to solve the overall problem optimally. But if I now consider a partial problem, then the optimal solution of the partial problem should be part of the overall optimal solution. Let me show that for the example of shortest path. So let's say I have some graph not shown here. I only show nodes S and T, and I want to go from S to T, traversing edges in the graph. It's a weighted graph, and I want to minimize the sum of the edge weights that I must traverse. Now, I consider some intermediate node here called K, and if K is some node in the graph, we don't know if the very shortest path from S to T will go through K or not. But if the shortest path does go through K, then the shortest path from S to K must be part of the globally optimal shortest path. Because if there had been a shorter path, let's say from S to K, then in the overall path from S via K to T, then I would also have used that red one. Yeah. So this is an example of what I mean when I say that the optimal solution to a partial problem must be part of the overall optimal solution. All right, and secondly, it only makes sense to use dynamic programming if indeed you can reuse the solutions to subproblems. So for example, on the right-hand side, in going from S to K, we also have to solve the shortest path problem, and we will do that via an intermediate node, let's call it L. And then the shortest path problem from S to L will involve computations that we anyway need downstream. So we want to be able to, it only makes sense if the problem necessitates solving the same subproblem over and over, and rather than resolving the same problem over and over, we remember its best solution in dynamic programming. All right, this was very generic. Now let's look at algorithms. So the length of a path today is given by the sum of the edge weights, and then there are two famous algorithms. One is if applicable if a graph has no negative cycles. So what do I mean by that? The edge weights can be positive, which means we have to pay something if we traverse the edge. Edge costs can also be negative, which means you actually get a reward if you traverse that edge. Now, if somewhere you have a single, if you have all right, let's say I have an edge here with a cost of -10. So I get a reward if I traverse it, and let's say the other edges here are positive, it's not a problem if I incur a reward somewhere along the path. But now it could be that I have a cycle, and for example, as long as I have here costs of plus 20 and plus 5, no shortest path is going to have the idea to revisit the cycle several times. But if on the other hand the costs here are only let's say plus 5 and plus 2, then if I take the cycle once, I make a net win. Yeah? So by walking along the cycles once, I've made a net gain of 3 units. Being greedy, well, I would use that cycle again and again to incur that reward again and again. So this is an example of a negative cycle, and this is an example where Dijkstra's algorithm would not be applicable. And I will show it in a demo in a moment. The other famous algorithm is Viterbi algorithm. This one simply says, all right, you got a cycle like here, then I am not applicable. Yeah. So what is and what is not a directed acyclic graph? So this is fine. This graph, if we ignore the arrows, to us it looks like a cycle. But if we do take into account the arrows, then you cannot come back, to a node by only walking or by only following the arrows in the proper direction, and hence this here is actually a directed acyclic graph. And then Viterbi algorithm works. Now Viterbi is maybe a bit simpler to understand. Let's start by looking at that algorithm. So I've taken this example here from a very nice book by Simon Prince, which is also available online. And so what we want to do is we want to start from a node S to a node T, and we have here initially edges of 0, weight, and also at the end we have edges of 0, weight. And now you see, of course, that this graph here, it's not just a random graph. It is super highly structured. It is very regular. This is also called a trellis or a lattice. Now, why do we consider such a super highly structured example here? Because these trellises and lattices, because they arise routinely in applications, as we will see soon. And so hence we're going to study how Viterbi algorithm solves the shortest path problem on this trellis. Now we have here nodes that we want to visit. We have edges that we can only traverse in the directions of the arrows. We see costs associated with these arrows. So for example, if I take this edge, I pay a cost of 0. If I take that edge, I pay a cost of 2 units. And also I incur further costs when traversing a given node. So for example, if I go through this node, this slaps a cost of 1.1 units on my path. All right, so we want to find the shortest path from S to T. Obviously, there are very, very many such paths. Looks like a hard problem. But what Viterbi proposes is the following. So here in the first step, well, after traversing these edges of cost 0 and reaching these nodes, which you see have respective costs of 2, 0.8, and so on. After this first step, we have incurred these costs that you see written in these nodes. So let's say here if n, for example, is time, if I interpret this as time, then at the first time step, well, my favorite state, and if I interpret this here as different states, then my favorite state would have been this one. Let's peek ahead. Actually, in the final solution, I think the didactics of this example are not perfect, because here in the globally optimal solution, well, actually, the optimal path does go through that edge. But this is not a totally greedy algorithm. So in general, at this point here, I cannot conclude, so far as we have computed now, I cannot conclude that this is really going to be the best state at the first time. Why not? Example, let's say that you see these costs here, they're always here, numbers below 10, let's say. Yeah? But if I had now given this here an edge weight of whatever, you know, 1,000,000, and this edge weight here would be 1,000,000, and this edge weight would be 1,000,000, then well, clearly any path going through that node would have a weight of at least 1,000,000. And you can perhaps already guess that we will find cheaper paths in here. Yeah? So yes, at this stage, it looks like this is the best state. And in this particular example, this will turn out to be part of the shortest path, but that need not be so in general. All right, so these are our best costs so far. Now, let's look at, now comes the interesting bit, okay? Let's look at this one here, let's say. You know, what is the costs, what is the lowest cost that we incur to get to this node? Well, I could right, let me pick a different one. I'm going to take this one because it has a cost of 0 associated. It will make my math a little simpler. So I could either reach it by taking the node with a cost of 4.3, cumulative cost of 4.3, and adding a 2. So if I take this one, I would reach this node via this route, and that would give me a cost of 6.3. Or I could reach the node via this route, which would give me a cost of 6.4 actually, because, well, it was 6.4 plus 0, that gives me 6.4. Or I could have reached it via this route here, 2.3 plus 2, overall makes a cost of 4.3. Now, to reach this node here, now let's call it K. Assuming that we want to go from S to T via K, well, which path would you choose? Obviously, the cheapest one. So the one which goes here and has a cost of only 4.3. And I now note that my new cumulative cost for this node is a 4.3. All right. And I do similar computations here for all other elements in this row. Now, at this stage, I can or cannot choose, or at this point, I can choose to remember, well, how did I reach my node K? Did I reach it from here or to there or from there? And here I can choose to remember that, yes, I'm willing to add that amount of extra storage and to remember that this was the cheapest path leading up to that node. But I can also, if I'm severely memory constrained, I can also decide to not do that and to just remember that the cumulative cost here is 4.3. And if I have the edge weights and I have the cumulative costs for the nodes before, if I store only those, and then that's enough to figure out afterwards, all right, which was the cheapest connection, which is called a backward pass. All right, so we've seen how to compute the best cumulative costs for this column, and then we go on and compute the best cumulative costs for the next column. And if you do this for a few more times, then we end up with the best cumulative costs even for the last column. Now we wanted to find shortest paths from S. There was a cost of 0 here, to T. And these final edges also had a cost of 0. These are cumulative costs, so which one looks best? This one looks best. And now we trace backward to see what was our shortest path, and that's the one shown here at the bottom, the shortest path. All right. This was Viterbi's algorithm. Do you have any questions for that? This was Viterbi's algorithm, defined on directed acyclic graphs. And if you do have cycles, well, then we would use, for example, Dijkstra's algorithm. And I don't want to talk about it now, but you can later look at a nice demo here. So finally, let's look at the pseudocode of Viterbi algorithm. So first, we have to topologically sort the vertices of G, which means we have to bring the graph in some order. If I have a trellis like so, well, you know, the order is trivial. I just go from left to right. But of course, you may have more complicated directed acyclic graphs. Yeah? So let's say this one here. Is also the directed acyclic graph. It's pretty obvious to us as humans how to sort the nodes. But once the graph gets bigger, even for a human, it's no longer you know, obvious to see what's the ordering here. So we need to first topologically sort the vertices, which in itself can be seen as an instance of a dynamic programming problem. And if you want to look at topological sorting, which happens via depth first search, then you can look at that demo or at that course later on. I've given just the link to all the slides in this nice algorithm data structures course in the literature tab of today's notebook. All right, so we first sort the vertices of G, and we initialize our search at a node S, and then we visit each node of the graph, each vertex of the graph in topological order, and then for any edge VU in the forward star of V. So what does this mean? We have a node V, and we have incoming edges. That's the backward star, and we have the outgoing edges. This is the forward star, or here called Fs of V. So now we consider these outgoing edges, and then we, so this is V, and then one of these neighbors here would be, let's say, a node U, And then we use this equation here. The distance of node U to the source is given by the minimum of the current best estimate that we have for this cumulative cost and the new estimate, which is the cumulative cost of V plus the cost of transitioning this edge here. So this would be W of E, would be that cost. And this is exactly the consideration that we used here. So let's say we first try out this path. It gives us a cost of 6.3 associated with that node. And now we visit it at some point later, and we find that actually I could also get there with a cost of just 4.3. So I update that cost. So this update is exactly what's written here. I take the minimum of my current best estimate and the new possibility that I have just found. And well, this equation here, which I hope is understandable, is written in a different format here, and we see these funny symbols. That has to do with these semi-rings that we will visit later in the lecture, not today. Good. Any questions? All right, then we will look at more detailed modeling of these shortest path problems after the break.